today's problem from power series of real analysis, right? And the problem is assuming the power series expansion for 1 plus x square whole to the power minus 1 as it is given as 1 plus x square whole to the power minus 1. This is equal to 1 minus x square plus x to the power 4 minus x to the power 6 to so on. Obtain the power series expansion for tan x. Okay, so we have to find the power series of tan inverse x using the power series expansion of this. And also we have deduct two result from this result. Right. Now we first, in this type of problem, we first find the radius of convergence of the power series. Okay. So to find the radius of convergence of the power series, if we write the power series 1 plus x square whole raised to minus 1 summation n, this is equal to 0 to infinity and minus 1 to the power n into x to the power 2n, and we get the given series in compact form, right? So comparing with the power series n, this is equal to 0 to infinity an x to the power 2n, we get here an, this is equal to minus 1 to the power n, right? So we use the formula of radius of convergence. This is 1 by r. This is equal to limit n tends to infinity mod of an plus 1 by an, and this gives limit n tends to infinity. This is obviously 1, because if we put the value of n plus 1, then minus 1 to the power n plus 1, and the lower is minus 1 to the power n. So this is limit n tends to infinity mod of minus 1. This is equal to 1. Hence radius of convergence r, this is equal to 1. Okay, we find the radius of convergence here. Now we know that in the interval of convergence, what is the interval of convergence? The interval of convergence is mod x less than r. Okay, and here r, this is equal to 1, so interval of convergence is mod x less than 1, or it is also said to be the region of convergence, or it can be written as open interval minus 1 to 1. This is the interval of convergence. Okay, now in this interval of convergence, if we take any bounded closed interval, okay, that is, if we take any bounded and closed interval AB in the interval of convergence, okay, then power series give permission to term by term integration and term by term differentiation. We already get the theorem of power series as this. Okay, we again say this theorem: if we take any bounded closed interval in the interval of convergence of any power series, then we can integrate or differentiate term by term of the given power series. Okay, so we here get closed and bounded interval as 0 to x. This is a subset of minus 1, 1. Okay, now here we get the power series like this, and we integrate both sides in the interval 0 to x term by term, and getting the result as integration 1 by 1 plus x square dx, and the range is x equal to 0 to x, and the right side is integration 0 to x 1 dx minus integration 0 to x square dx plus integration 0 to x to the power 4 dx and minus so on. Right? This is the theorem of power series. Now integrating, we get the result as this is tan inverse x. This is the formula of integration, and we put here the range 0 to x. And this side is given by the first term is x, and the second term is x cube by 3. We directly put the limit of integration plus x to the power 5 by 5 minus x to the power 6 by 6 plus and so on. Okay. Now we put the limit on the left side also. We get here by putting the limit x, we get tan inverse x, and by putting the limit 0, then we get tan inverse 0. That is minus tan inverse 0. Okay. And tan inverse 0 means we know that this is 0 also. So we get the result as tan inverse x, this is equal to x minus x cube by 3 plus x to the power 5 by 5 minus x to the power 6 by 6 and so on. Okay. And we get the power series of tan inverse x, and this is our first required result. Okay. So we already obtained the power series expansion of tan inverse x. Now to deduce the first result, okay, we put x equal to 1 on both sides of this result, and we get tan inverse 1, this is equal to 1 minus 1/3 plus 1 by 5 minus 1 by 6 to so on. Okay. And tan inverse 1, this is equal to pi by 4. So we get the result, this is equal to pi by 4. Okay. So we deduct the first given deduction. And now to deduct the second deduction, we first divide both sides of this series by x. Okay. And get from here as tan inverse x by x, this is equal to 1 minus x square by 3 plus x to the power 4 by 5 minus x to the power 5 by 6 and so on. Okay. And here we see that this is also a power series of tan inverse x by x. If we find the radius of convergence of this power series, then it is clear that the radius of convergence of this power series is also be 1, because we get this power series by integrating term by term from this power series. And it is a important theorem or important information of power series that if we get another power series by term integration or term by term differentiation, then the radius of convergence is not changed. Okay. So the radius of convergence of this power series, we say that this is also 1. Okay. Now we integrate this series again in the interval 0, 1. We get the result as integration 0 to 1 tan inverse x by x dx, and the right side is integration 0 to 1 dx minus integration 0 to 1 x square by 3 dx plus integration 0 to 1 x to the power 4 by 5 dx and so on. Okay. And integrating, we get this is 1 minus this is 1 by 3 whole square plus this is 1 by 5 whole square minus and so on. And the left hand side becomes 0 to 1 tan inverse x by x dx. And clearly this is our second reduction. Okay, this is our second reduction. So we prove the second reduction also. Okay, this is very easy problem but important problem of power series. Thank you for watching.